Thank you very much. Yes, I forgot that. Okay, so thank you very much for the very kind invitation for this school. And by the way, you guys have done a tremendous job, so congratulations to you guys. I mean, this is really something, yeah. It's really remarkable what you guys are doing. So, okay, that's the title, Aspects of Perturbative Quantum Gravity and Celestial Holography, which is an attempt to try to do flat space holography or to try to put in some more rigorous mathematical terms the hope that quantum gravity could be also, there could be a precise description of quantum gravity in asymptotically flat spacetime. That's what basically that effort is. So I'm going to write what is the objective of these 3 lectures that I want to give, and then I'm going to write an outline with more detailed steps about how I intend to do it. So it's basically two things that I want to show. The first thing is I'm going to write it down, everything. So I'm going to show some remarkable computations that that people have done, in the past. Some remarkable aspects of quantum gravity, but I put in parentheses perturbative. Because by perturbative, of course, Feynman diagrams at the end of the day. We're going to be computing scattering amplitudes of gravitons in some theory, a favorite theory, be it Einstein gravity, or even a string theory. I'm going to show computations in these two theories, and I'm going to show some universal aspects of these computations that are pretty remarkable that people have done in the past. So, quantum gravity, and not only that, I'm going to focus on 2 very extreme cases, which is the case of extremely low energies. In other words, that's called soft, the soft regime, and in the opposite regime, in the full Transplanckian energy regime, also called the deep UV, the deep ultraviolet. Okay. So here it goes. Two extreme regimes. So the infrared is going to be ultraviolet. So in short, the IR and the UV. Okay. So I assume that everybody is like in master's or doctoral. Are there any licenciatura? Yes. Okay. Have you guys already taken quantum field theory? Yes. Okay. GR, of course. Yes. Also, okay. How about the what's it called? Física de partícula. Yes. Particle physics. Okay. All right. Okay. So, and then my other objective is to an introduction. So they asked me to talk about celestial holography. So here it is. Introduction to flat space. So flat space, also known as celestial holography. And I'm going to show that this particular program, celestial holography, So fast-spaced holography, if you will, and show how. I'm going to write it down. Show how this. Can you say novel? Novel. It's been 10 years almost. Okay, so it's not really that novel, but okay, it's recent. Just with respect to some scale. How this novel approach precisely mixes the IR with the UV, or and the UV, the IR and the UV. In a way that I don't have handwritten notes. That's why I'm writing everything. So, in a way that 3+1 bulk physics, and maybe bulk physics is too much of a ambitious name. What I want to describe is scattering amplitudes that usually you would see the effects on collider physics. And then how this can be rewritten in a way that looks like a conformal field theory correlation functions on a 2D theory. Basically, the idea is that is a CFT also that lives on the celestial sphere. Hence the name celestial. Okay, but I would say more about all this probably in my second lecture tomorrow. Okay. Okay, so that's it. So that is the objective of these 3 lectures. So I'm going to read it again. So the idea is that the way in how this program is built upon scattering amplitudes that you really measure in the experiments at the end of the day, they can be rewritten in a form in which they look like correlation functions, or they become correlation functions in a 2-dimensional theory. That theory has all the basic aspects of being correlation functions in a CFT. That theory lives in a 2-dimensional sphere, which is basically the celestial sphere in which when you have a scattering experiment, particles come in and particles come out. They come out and they just pierce, they're like in the sky, where you put your detectors, right? So those piercings, they'll become insertion of certain operators, and then correlation functions of these operators reproduce the scattering amplitude or the physics that occurs, deep in the in the scattering process at tiny distances. Okay, so in that sense, you may want to say that this is holographic, but let me just. I'm going to start with what's called the S matrix, in which the S matrix. This is from the 1930s, 30s even. You could have also said that the S matrix was, in a sense, also a holographic object. Okay, so that is basically the idea. Okay. Okay, and then, the CCFT is what people have coined the celestial CFT. Okay, so this is the outline of. So I'm going to First thing is I'm going to introduce, and I know many of you already know these things, of course, even from non-relativistic quantum mechanics in undergrad. As an undergrad, we learn about scattering amplitudes or scattering processes even in the Schrödinger equation, right? So, but of course, I'm going to focus on relativistic physics. So, but yeah, this is also known for many of you. So I'm just going to give a very brief review of the scattering amplitudes. And so basically I'm going to focus on an object, which is called the S matrix. And also I'm going to say a little bit about kinematics. Okay? Just basic kinematics, basic relativistic kinematics that you can find in Griffith's book, for example. And I'm just going to show a simple example in QFT. Okay? So this, I should be done with this today. And the next thing I'm going to talk about is a remarkable set of results that Weinberg came up with in 1964, 1965, which are called the soft theorems. Okay, and okay, I'm not going to write anything. But by soft, we mean very, very low energy, so we are in the infrared region. Okay. Then 3, I'm going to go to the opposite extreme limit, which is the UV, deep in the UV. Okay. So quantum gravity. I'm not going to write perturbative quantum gravity, but okay, that is assuming all these 3 lectures that I'm only going to say things about perturbative computations, meaning amplitudes again. And by extreme high energies, I mean energies even bigger than the Planck scale. Okay, there's a common law that the Planck scale is like a upper limit of the energy. That's not true. I mean, there's no impediment for defining things, you know. Of course, you need a theory of quantum gravity, right? Yeah. That's a given. But in principle, there's no obstacle for going, you know, as high as you want in energy scale. As is, there's no limit in how low can you go in energy scale. Okay. So, and this I'm going to show two remarkable examples. Black hole nucleation or black hole pre-production. Let me just say a few things. And then one thing which is I find really, really nice is that so I'm going to show a computation in which you can kind of infer how the scattering amplitude what is the probability for the creation of black holes, and that is it gets imprinted in this object called the scattering amplitude, or the S matrix to be more precise. By the way, S matrix is the same as scattering amplitude but on shell. Okay, so scattering amplitude, you can define the scattering amplitudes off shell in the sense that the particles that you define, the vertices, the Feynman diagrams, whatever you like, the objects can be off shell. Okay, but the S matrix is the physical thing, is the real thing at the end of the day. So those particles, since are free, they have to be on shell. They have to satisfy some dispersion relation, which of course in the case of kinematic, relativistic kinematic, we know that E goes like the square root of P squared plus M squared. So that's basically what I mean by on shell. Okay, so, and what I want to show is that I'm going to show some a computation that have been done by many people like Tov, Giddings, and there are many computations that even Weinberg of how, for example, you can show that you can create black holes if you scatter two particles at very high energies. If these energies are larger than for example, the scale set by a Schwarzschild radius, then you will produce a little black hole there, right? Or these energies may not be too high, but if the impact parameter is also or is higher or is smaller actually than the Planck length, then you also are in the regime in which it becomes more likely that all the intermediate state that you're creating in between are black holes instead of just pair creation of electron-positron pairs and things like that. Okay, so and I'm going to show how that assumption gives you a certain behavior of this amplitude, which is actually the same as the behavior that you find in string theory at high energies. Okay, so here there's no strings whatsoever, but this behavior is also the same that you find for strings at high energies. Okay, so that behavior, I mean, you can read it. I mean, if you're like really for string theory, you would say that this would be a kind of a evidence for that the string theory is correct. Or you can say the other way around, which is a little bit more conservative, in the sense that okay, what you find at high energies, you're actually finding some universal behavior of quantum gravity, whatever your favorite quantum gravity theory is. Okay, so that's basically the message. Okay, and then. Okay, so that will be my last thing. So I'm going to show how to compute these celestial amplitudes, or these things called celestial amplitudes, which is just another name for correlation functions, but that are obtained from these scattering amplitudes that occur in 3+1 bulk physics in flat space. I'm going to show a computation in field theory and also in string theory. And you might ask this question right away. Okay, since there is this soft theorem for the scattering amplitudes, do you have something similar for this new way of writing a scattering amplitudes in terms of this correlation functions on a 2D CFT? And the answer is yes. And these are called conformally soft theorems. So I'm going to say a few things about this also. And I'm going to say, time permitting, I'm going to say something very quick about what these are, what are called the W algebras. And here, I'm going to tease you with this. Okay, so let me just give you like a flash picture of what that is. So when you rewrite these scattering amplitudes in this new way, which is achieved through basically it's a Boolean transform. Okay, you find that this soft theorems that Weinberg discovered 50 years ago are written in a different way, and this new way has something to do, or it has a direct relationship with OPEs, operator product expansions, in a CFD. And then when you play around with these operator product expansions and you compute commutators, you see that a new algebra arises, and this algebra is called W algebra. So that thing is there; it's already there. I mean, this is pretty much kinematics. It's not something which is you can say no, this is wrong or whatever. It is there. But there's a little caveat that I'm going to show you. I will show you later. That this is in a particular sector of gravitative amplitudes. So it could be, this is still under development, okay? So it could be that when you include the full sector, by sector I mean helicity amplitudes and things like that. Maybe I will just very quickly mention these things later on. But it could be that all this thing goes, so this W algebra goes away if you include the full thing. It's very likely that that is not the case, and these things are really there. Okay, but this is, I cannot say something completely, this is set. This is set already. Okay, and this W algebra, as you can see, it's a lowercase w, because it's something that is found at the classical level, in the sense that at the level of tree-level scattering amplitudes for gravitational scattering. But W algebras have an extension, have a quantum extension, in the same way that the Reed algebra has a central, if you extend it with a central charge, you get a solar algebra. You have something very similar to that. So it becomes it's a very, with a big of originality. They call it uppercase W algebras. So the hope is that the full quantum version of this conformally of theorems would see these quantum deformations of these W algebras emerge in this competition. Okay? But I would not say much about that. Está bien cierto, son dos nomás. Okay, so I will stop the monkey business with just writing things. Let's do some computations right away. Okay, so taking the risk that I'm going to bore many of you, because maybe many of you already know this, but okay, here we go. I'm just going to do it. Okay. So of course, particle physicists care about smashing particles at high energies or at any energy and try to see what comes out. So we're going to label our particles with, I'm going to say that we have a scattering of n particles, so some come in, some come out, but in total we have n particles in this scattering process. But this is quantum mechanics. So quantum mechanics, right, this is the initial state. So we associate this a ket, what we call n, and then we try to measure. So we prepare a state that it's defined in t minus infinity, and then we try to compute an amplitude in which now we see, for example, we define this object called the out state, which is by definition it's defined at t plus infinity, right? And then what we want to compute, it's the scattering amplitude. Okay, not yet. So then what I want to do, of course, is in quantum mechanics, I want to do the bracket of in and out. That would be the amplitude of that process to occur, right? But there's a little caveat there, that in state is not defined at the same time as the out state. So I have to make it evolve all the way that, scatters here, crazy things happens, and then that in state has to evolve into the out state, and then I bracket it, right? So basically, what I do is at the in state, I try to make it evolve. So evolve with some operator I'm going to call S. So this is going to be defined now in T plus infinity, and then I compute that amplitude. Okay. So then the out bracket with the in state, which evolved in time, and this is what we call the amplitude. Okay? That is basically what scattering amplitude is at the end of the day. So if you're able to compute this for any theory that you like in exact, of course you get many Nobel Prizes, right? But that's this is computing this thing. This is the beast, right? And besides some very special cases, we have to resort to perturbation theory to compute this thing. So we have to come up with some small parameter in which you expand on as a Taylor series, a power series, and then each term in that sum is what Feynman, of course, it's what people call, of course, Feynman diagrams. If you want, you can add, if you don't want to use Feynman diagrams, you can just use the old-fashioned string of Dyson expansion, and you can do it that way also. But of course, Feynman diagrammatic it's much more pleasing to the eye and also more intuitive to compute. And as Julian Stringer used to say, that he despised Feynman diagrams, and he used to say that Feynman brought QFT to the masses. He was a very bitter person. Okay. All right. Okay, and of course this operator was extremely important, and this operator is no more nor less than what we call the S matrix. Okay, that is what the S matrix is. Okay, so the S matrix is pretty much evolution. It's pretty much what you would call an evolution operator. Even in non-relativistic quantum mechanics. All right. So usually, it's usually very convenient to separate the identity operator from the rest when you write down this S matrix operator like that. Because of course, again, since we're doing quantum mechanics, you have to include all possible, possibility of all possible outcomes. And one of the outcomes is that there's no scattering at all. The particles just go and miss each other and just keep going the other way. You have to include that, of course, into the total probability amplitude, right? So that is that number one. Is therefore, so when you open up any QFT book and you compute amplitudes, what you're really computing is this guy, okay, not really the S, okay. Sometimes called the transition operator or transition amplitude operator, okay. So so since I want to be as pedagogic as possible, let me, if you allow me, I'm going to do a very simple example of non-relativistic quantum mechanics that when you solve Schrodinger equation with some kind of potential, square well potential or whatever potential, okay? This is just to introduce the concept or just to remind you of the concept of the S matrix, okay? But I promise I will not take more than 5 minutes to do so we can move on. Okay. Okay. Okay, so you open up your favorite quantum mechanics book, and you go into this. You go into the chapter of scattering amplitudes. And then a typical example you have, for example, a one-dimensional problem. Let's just do that. You have a potential, and then this potential, has some shape, whatever shape. But the important thing is that in order to be able to define free states all the way there and all the way here, you need the potential to go to zero at some point, right? It has to have some kind of a compact support, or it has to, go. Maybe the support doesn't need to be compact, but it has to go to zero sufficiently fast at x plus or minus infinity. So what is the usual thing? Yeah, you define, for example, you separate these regions, right? As usual, region 1, region 2, region 3, and then in region 1 and 3, you assume that you already have free states. So I write the wave function here as, let me follow the same. So you have, what you have? So I have a plane wave moving in that direction. So ikx, and then you have. Okay, let me just not finish that yet. Okay, and then you send also, for example, a particle from the other way, and they scatter, produce something here, and then come out on the other way. So that's what I want to describe. So I have this coming in. This is also coming in. Let me call it b e to the. Now this is going to the opposite direction, so it's minus a kx. And then after the scattering, occurs, something comes this way, and something comes this other way. And let me call this c minus I kx, and this one is c, so d I kx. Okay, so in region 1, the wave function is going to be a superposition of this and this. And in region 3, you're going to have a superposition of this and that one over there. Right? Then you put it in the Schrodinger equation, you do matching conditions, you assume that the wave function is normalized, blah, blah, blah. You solve the differential equation. And at the end of the day, what you arrive at is that now I'm going to write it in a different way. Now this wave function n is going to be a superposition of this one here and this one here, right? Because these are the particles that are coming in to the scattering experiment. So it's going to be another linear combination. So this A plus B, that. And then the other state that we call out, of course, is the linear combination of this one and this one over here. Right? We're not very used to writing this way. We're used to writing this way and solving the Schrodinger equation and so forth and so on and so forth. But in order to make the connection with what this matrix really is, let me rewrite it in this other way. So we're going to have C minus plus D Okay? So at the end of the day, what we really want is I want to find C and D in terms of A and B, right? I give you the initial state, the initial particles, and then I want to see, what comes out. So I basically want to know what C and D are. And then since Schrodinger's equation is a linear equation, then you're going to find a linear relationship between C, D, and A and B. And let me call these elements S11, S12, S21, and S22. And this is what you call the S matrix in relativistic quantum mechanics. So it's just a 2 by 2 matrix because you have just a few numbers, but you get the idea. When we do scattering in relativistic quantum mechanics and in QFT, then you have creation. You have also many labels. Particles are labeled by the favorite quantum number that you want to use. Since you have relativistic physics, then you choose energy, momentum, also charge, electric charge, color charge, whatever you name it. Whatever labels you want to put on. And let me just say one little thing. And then your S matrix in QFT is going to be like an infinite dimensional matrix because you have infinite set of numbers basically. But that's pretty much. I'm sorry, go ahead.
The information of the internal momentum in the scattering process is in the S matrix.
The information about what?
The internal momentum.
You mean internal? What do you mean by internal momenta?
The momenta who appears in the Feynman rules. The QS.
I'm not sure. I mean, you mean in this example, or you mean like in the true?
Yes.
Oh yeah, the S matrix. Yes. That has all the information about. More precisely, more specifically, instead of momenta, you need Lorentz invariant quantities constructed out of the momenta, and these are called Mandelstam variables. So the S matrix, it's a function, it's an analytic function actually of these Mandelstam variables, and more stuff, like for example the helicities, with all the spins of the particles and things like that. Does that answer? Okay. Okay, so I will go exactly into that now. Can I?
Hasta las 5:25.
5:25? Ya. Gracias, Mike. Revisar a terminar. Yes, kind of. Okay. So we said that we were going to talk about the kinematics, and here. The basic objects are called the Mandelstam variables. Stanley Mandelstam was a South African physicist. He was, as many of these people were geniuses. Let's focus. So just a quick poll. How many of you already have, know and have worked with Mandelstam variables? Pretty much everyone. Okay, cool. Thanks. So let's focus in sort of the simplest kinematical case of scattering, which is two go in, two come out. Actually, the simplest would be three, right? Like pair reaction or pair annihilation. But this has a lot more structure. So let's do this. So the Mendelssohn variables are this and these. So of course this is Lorentzian square, and since it's a square, you right away see that S, T, and U are Lorentzian invariant quantities. And in general, the amplitude is a function of these Mendelssohn variables, and as you can see, I wrote it only as a function of 2 ST and not U, because you can check. So little homework problem, you can check that S plus T plus U is equal to the sum of the masses of the 4 particles squared. Okay, you can check that. So in particular, for example, when you have masses scattering, if these are graviton, or graviton, photon, graviton, whatever, if the states are masses, this sums to 0. And although that's a very trivial observation, has a lot of consequences in many of the things that I would like to show you in these lectures. Okay. Yeah, let me say, let me call this like that, just straight A, and the full amplitude is, let me write it with a cursive. Okay. In reality, it has also a momentum conserving delta function. That I'm sure that many of you already know that. Okay. And so this comes from. So the fact that total momentum of the scattering process is conserved is a consequence of. Since this is a school, can I ask questions to the audience or no? Yes. Okay. So where is this coming from?
Conservation.
Yeah, but conservation momentum is consequence of what?
Energy.
Translation invariance, right? So this comes from the Poincaré, or the translations. Space-time translation, right? Space-time translation invariance. And the fact that the rest only depends on Lorentz invariant, this just comes from the Lorentz invariance, right? So, and the full thing is called, what's the name of the full thing? Translations plus the Lorentz group? Okay, I forgot my disclaimer at the beginning of these lectures. since I want to show my idea for these lectures is not to like show one particular topic and develop it and give you all the details about it. That would be nice, but I chose a different approach. I chose the approach of like showing you different computations, which I think they're really nice to see. But okay, since there is only limited time, I'm not going to be able to show you all the particular details of how you get into all these results. And I'm just going to show you a flash, what the steps that go into those results. Okay, so yeah, that's my disclaimer. Okay, so let me just show you how to gain a little bit of intuition on what the physical meaning is of these Mandelstam variables, which are Lorentz invariant. Since they are Lorentz invariant, I can compute it in any frame that I like, right? So one particular frame, which is very useful in order to visualize a little bit what these mean, is the center of mass frame, okay? So the center of mass frame, yes. Yeah, in order to visualize a bit the physical meaning by the way, the Mandelstam variables, I just wrote them, of course, for the case of 4 particle scattering. Of course, this has a generalization for n particle scattering. Okay, it's just it becomes more cumbersome, but that's it. Okay, so in order to visualize a bit the physical meaning of the Mandelstam variables. So let's compute them in the center of mass frame. And so the center of mass frame is by definition the frame, when you study in physics in the first physics course, is the frame in which the spatial momentum add up to 0, right? So this is a 3 vector. 3 is a 0 vector, okay? So that is basically the frame. So if you want to visualize it, of course, in a little diagram, then you will have to draw it like this, such that the sum is 0, something happens, some scattering, and then something comes out. Notice that I'm still writing the little arrows on top of them, so this is 3 momenta, and so you have some scattering angle, and this is called the center of mass scattering angle. So let me compute S. So S, what is S? S is by definition that. By the way, you might see it in the books with different notation. For example, some people write it with the plus sign here. There's no minus sign here, and that is basically because they're using the bad metric. They're using the mostly plus, mostly minus metric, but we're going to use the good one now. We're going to use the mostly plus, so minus, plus, 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 okay? Of course, that's true. And, you know what they call it, the West Coast and the East, the Americans, they call it the West Coast and the East Coast. And the reason was that, for example, on the East Coast, it was Princeton and all the Wheeler boys. They were all doing gravity, so they were using the mostly plus metric. So that was called the East Coast metric. And on the other side in California, there was this lab, the accelerator, where all the particle physicists were doing experiments, and they were using the minus, minus, minus plus metric. So that's called the West Coast metric, according to the Americans. Okay? So okay, that's the history. Okay, so let me compute that Lorentz product. So this is what is it? Let me write it in So I'm adding this is 4 momenta, right? So I have the 0 component, and then I have the other 3 components, and then I square that vector. And by definition, this is equal to 0 in the center of mass frame. So, if I want it to be strictly rigorous, I should, since I'm writing already the momenta with some particular components, I should say in which frame we are, right? So I should say center of mass, center of mass, center of mass. Okay, but that's too much letters, so I'm not going to say it. But of course, you know that I'm referring to one particular frame, which is the center of mass frame. So we get that, and then since we're using the good metric, this is going to be plus E1 plus E2 squared. Okay. So notice that the Mandelstam variable S here is positive. So and since this is just the addition of the 2 energies in that frame, the physical meaning of the Mandelstam variable S is simply the center mass energy squared of that scattering amplitude. Okay, so if you see these usual plots that people when the particles physicists claim glory and they find a new particle, they have like a graph like this and then a little bump, right, at some square root of S. So that would be at some energy of the center of mass. So when they see that bump, for example, when they saw it for the Higgs, they found this bump at what was it? I always forget. 126 GeV. Is that the Higgs? We're using the good metric, so that's why we know how this stuff. So they see a little bump, and yeah, I should have said this a little bit later on, but that's basically when you see in those plots they have square root of S. Of course, they mean that. Okay, they mean the center of mass energy, which is at the energy in which you have this resonance of some internal particle, being produced in that scattering, and this is when they yell Eureka. Okay. What about T? Let's compute T. So T is minus P1 minus P3. So, and here I always forget, what is this here? And this is a shorter way of doing the computation. Okay. Yeah, so here I'm going to expand this block. So here I wrote it in components and then I square. Here I'm going to square right away, okay? So this is minus P1 squared minus P3 squared plus 2 P1 P3 Lorentzian dot product. And so since we said from the very beginning that we were going to consider only real particles, right? Not virtual particles. Real particles, so they are on shell. So pi squared is equal to minus or plus mi squared. Minus or plus. The best way to remember this is that this is this relationship we learned from very young age, and that's even before one learns relativity. So so if you want to write it in the mostly minus metric, then you would write this, right? And this has to go to the other side. So this is what we call p squared in the mostly plus metric. I'm sorry. So p squared is minus pi. So here we have minus minus. We have m1. So the mass of the particle number 1 squared plus the mass of the particle number 3 squared plus 2 p1 p3. If I'm boring you with these details, let me know, and I can just skip it and go on. Okay. Nunca lo vendí esto.
Está grabando de ella.
Sí. Voy a vender ahora. Voy a prender ahora. Ok, perdón. Bajaron. Ya. Okay, so I don't want to. Let me continue here because I don't want to erase. I mean, I don't want to cover that. Okay, so T we get on 1 square. I mean, this is all in the first pages of any of these textbooks. So here we have 2, and then minus P1, P3. Here I'm doing the Lorentzian particle maybe. So plus P1, P3, 3 of that. Okay. So and you see that the angle is already. I should have not erased it. So this one P1, this was P2, that was P3, this was P4. Now we're the center of mass angle. So you see that is going to have the cosine of that angle over there. So the T has information about the energies of the scattering particles and also the angle. So it has a twofold information. Let me just write it in the massless case. Since we're going to be focusing on massless scattering, because we will be doing gravitons a lot. In the massless case, there's a simple way of writing this thing. So T, this goes away. You have minus 2 E1, E3, plus, so this is going to be absolute value of 1 times absolute value of 2 times the cosine of that angle. And since the particles are massless, then this is basically, and this is E1 and this is E3, right? And then you can factor that out. I think I made a mistake. A sign.
This is minus.
This is minus, right? Yeah, minus 1. Thank you. So then I can have minus 2 E1, E3, 1 minus cosine of that. Okay? So that is the meaning of, in the case of the massless case, you see that the physical meaning of T has information about the energies and the angle. And notice that in the literature, there's it's a kind of a hot topic right now, which is called the graviton pole problem. I don't know if you've heard about this. There have been many papers being produced in the past couple of years, which is called the graviton pole. The graviton pole problem. It has to do with the fact that it's no surprise that gravity dominates the scattering processes or physical process at the time scale. So when energy is very high, you know that quantum gravity dominates there. But it also dominates in another regime, which is in the regime when this goes to 0. When this scattering angle goes to 0, you see that basically you have like the particles, more like that. That's called forward scattering. So it's barely any deviation from the original scattering line. And so that angle goes to 0. You get 1 minus 1, you get 0. So in the Feynman diagrams, when you compute, you usually have poles in the T channel. So even for moderate energies, for that angle, you have that the amplitude flows up in that case. So yeah, there's still an issue how to deal with that, because you have an infinity that you were not expecting at any energies. It only has to do with the scattering angle. So that's still a problem even today. You might think that this could have been solved 50 years ago, but no, it's still there. Okay. Okay. So let me just say that when this angle goes to 0 and T goes to 0, this is called forward scattering. Okay. There's a, let me do a little parenthesis. I'm just improvising this, but I think this could, this is a nice thing to. So the S matrix, remember that we were decomposing it like that. And remember that we said that the S matrix has to be an evolution operator. Or at the end, the bracket has to be invariant under if you do a unitary transformation, right? So that means that S dagger S, if you want to conserve probabilities, the probabilities have to add up to 1, you have to impose that into that operator. So written this way, you have 1 minus IT dagger, 1 plus IT dagger equals 1. So 1 plus I t minus t dagger, and then plus t dagger t equal 1. Did I do it correctly? I did it right? Yeah, it's correct. So this one goes away, this one's goes away, and then again t dagger t equals I t dagger minus t. Okay? So that's very basic algebra, but it has to be it has to be a very deep meaning. It has like a shark has sharp teeth. So we said that we're not, powerful enough to compute these these amplitudes, exactly. We have to resort to perturbation theory. So we have to do Feynman diagrams. We have to compute amplitudes in Feynman, using Feynman diagrams. And then remember that we said that T has to do with the scattering itself. So the possibility of just the particles missing each other is already in this one. So this has all the information about the interaction, right? So very diagrammatically, I'm saying that T is a function of the coupling constant. It's not proportional. Some function of the coupling constant, and when the coupling constant goes to 0, that T goes to 0. That's all I want to say. But this depends on the coupling constant, and since we're doing that Feynman diagram, this is going to be a power series in G. Okay? So notice a very simple observation that you can derive already. A very deep observation that you can already derive from this very simple equation over here. T is going to be decomposed in 3-level, 1 loop, 2 loop, 3 loop, and so on amplitudes, right? So, and also here, right? So notice that since this is of order 1 in G, this is of order 2 in G. When this is of order 2 in G, this is of order 3 in G, and so on and so forth. So what this is saying is that there's some connection about 3-level amplitude and one loop level amplitude. 1 loop and 2 loops, and so on, right? So this is called the optical theorem. You write it in a more sophisticated way. You bracket it with in and out states, and you derive some very nice and ugly formulas for scattering amplitudes using this. But what I want to say is that okay, two things. One loop amplitudes usually have divergences coming from the momentum over the loop, right? And usually these integrals have infrared divergences, meaning when the momentum goes to 0, and ultraviolet divergences when we're in the upper limit of those integrals, right? The ultraviolet divergences by now are mostly taken care of by in renormalizable theories. But infrared divergences is still an open problem. Okay? Even at the level of cross sections, which is the things that we measure at the colliders. Okay, I'm not going to go into too deep into that, but let me just say that there's a very nice thing about the optical theorem in the sense that this is at the level of the amplitude. Okay, this T is at the level of the amplitude. When you compute a cross section, you square the amplitude, right? And then you integrate over all possible external momenta. So basically, you integrate over the entire the solid angle, the three-dimensional solid angle. So when you do that, there are these things called collinear divergences, which appear precisely when this angle goes to zero, because in the cross section at the end of the day, since you have to integrate over this scattering angle, you have to integrate over this angle. So at some point, this angle is going to touch zero. So that is going to produce a divergence in that interval. So even at tree level, okay? Even at tree level, you're going to have, for some theories, that have massless states in the spectrum, like photons, for example, they have these collinear divergences. Now, those collinear divergences are going to appear from these things at tree level because of this theorem are going to be cancelled out. Are going to be cancelled out by loop divergences at one loop. Okay, so okay, I'm not boring you with these things, but I just want to I want to tell you that this very simple computation has very deep consequences in physical observables at the end of the day. All right. Okay, I promise it's going to get more exciting, hopefully. And while I erase, let me say one more thing that okay, now I'm going to write it down. So he was what was okay, so notice that S is positive and T is negative, right? This is always positive, so this is always negative. The energies are always positive. Okay, so this thing is called the physical scattering region. This is called physical scattering. Okay, and then you might say, well, okay, you're not saying anything deep, but what Mandelstam and other people discovered is that now, okay, so S and T were always real numbers, and S is strictly positive and T is strictly negative. What Mandelstam and other people in the 60s devised was that, okay, the scattering amplitude is a function of these variables, S and T. What if we just, embrace the possibility that because this is scattering amplitude, because they were meromorphic functions in the sense that they have simple poles in S and T and in U, because they have simple poles, it had all the properties that analytic or meromorphic functions in the complex plane have. So Mandelstam and people said, what if we let this scattering amplitudes to be defined as complex functions in the complex S plane and in the complex T plane? So this is no longer, okay, this is the physical scattering at the end of the day, but as a mathematical object, you can define it in the entire complex plane. So what they showed, and this could be an entire semester of these things, is what he started was what's called the S-matrix program of the 60s that is being revived now in the last decades. That if you use all the machinery of complex valued functions, analyticity, Cauchy's theorem, all these things that you learn very early, in the career. They have deep information about things about, for example, locality or causality of relativistic scattering. So, and of course, they were basing all those observations in things from optics. At the very, in the last century, this what's called the Bright-Wigner formula. What is that name? Or a dispersion relation, complex frequency. There were people in the 20s and in the 40s and 50s. They were doing optics, quantum optics with in the complex plane for the frequency of the photon, for example. So they borrowed all that intuition into relativistic scattering, and this is what's called the S-matrix program. And it's basically that. Assume that this function is analytic or meromorphic. Is meromorphic in the complex plane. And then you can deduce many of the properties that we know that physical scattering should have, like locality, causality, and even unitarity. Okay, it's kind of written in terms of this complex properties. Okay, so okay, I'll stop there with my very very short review of scattering amplitudes and the S matrix and the kinematics. And now let me go into what's called the software. Cinco. Okay. Okay, so again, we're going to have some scattering process. And we're going to focus in the case, so we have a process of n particle scattering, or n+1, because the 1, so this is a m+1 amplitude. Okay, and the 1 is a very special one. Is we're going to focus in the regime in which we have a massless particle. So this could be a photon, graviton, gluon, whatever your favorite massless particle is. And we're going to study this amplitude in the case where that massless particle has very, very, very low energy, in the limit when it goes soft. Okay? So, for example, if we write this particle, if we put the z-axis, along the direction of that photon or that graviton, then it will have the form momentum will have this form, and of course the guarantees that it's massless, right? Q squared. Okay. So the limit when omega goes to 0 is what we call the soft limit. Okay. So, in QED, in this limit, okay, low in 1958 showed that the leading contribution to the amplitude comes from diagrams like this. We have something, even non-perturbative if you want. Okay, I'm not going to say anything about non-perturbative physics. I'm going to do just perturbative physics. But something very complicated could be going on there. So I'm taking advantage of the fact that many of you said that you have computed Feynman diagrams already. Okay. What Lowe showed that in the low energy limit, no pun intended. That's really what happened. In the low energy limit and the soft limit, he showed that for the case of QED, the diagrams that dominate in the limit when the energy or the frequency of this photon, the QED, we have only one massless particle in the spectrum, which is the photon. The rest of the spectrum is very simple. It's just the positron and the electron, and that's it. In that limit, he showed that the amplitude can always be written in a leading order. So if you do like a Taylor or a series expansion in omega, the leading term always corresponds to an amplitude like this, in which you see that you have an amplitude here. You have an amplitude in which it has the same external states as the original amplitude, but the photon is removed. Okay, so I'm going to write this as the usual or the original n plus 1. I'm just going to write a n, which just means the same as the n plus 1, but with the soft particle removed, times, and now you have to compute this amplitude. But this is a simple vertex that you can compute. This is a simple 3-level vertex that you can compute this in Feynman diagrams, right? But that's not only a vertex. Notice that there's also a propagator here. So it's a multiplication of 2 little things: that propagator and that vertex, and that's it. So I'm going to show you the computation in the simple case of not QED, in order to not deal with spares and anything like that. I'm going to do it in scalar QED, just the scalar field with a photon, coupled to a photon, and that's it. Okay, so example. Scalar QED, right? That would have just a U1 gauge field and a simple scalar field. Okay. If you want to, so in that case, for example, I'm going to need, look, oops. I'm going to need the propagator. This is the propagator of. Remember that we're doing scalar QED. So this would be, if it was real QED, this would be a photon, and this would be positron and electron. But in the case of scalar QED, it's just going to be a scalar field. So I need the propagator for that scalar. Okay. So the propagator for the scalar field, in a theory like that, the simple scalar QED, the propagator. With momentum k, let me call it momentum p. We're calling p all momentum. So it's going to be minus I p Okay, just the usual thing. But that's the mass of the thing. And then we're gonna need this vertex which is so scalar photon vertex. So this is I. There's an interaction strength here, which is given by the electric charge. So it's IE, and then you have to, this photon has momentum Q, and it also, since it's a spin one, it has a polarization vector, epsilon mu. Okay? So that vertex is given by that epsilon mu 2 times the momentum of the electron, or the scalar electron in this case, plus the momentum of the photon, and that's it. Okay? So that is that vertex. Okay, so let me just go ahead and compute that amplitude then. Let me do it here, because I don't want to cover that. So, the full amplitude, it's the multiplication of this amplitude and this amplitude. That basically stems from the fact that of the probability, right? If you have the probability of this thing happening and the probability of this other thing happening, the probability of the joint thing is the multiplication of two probabilities, right? So that the amplitude inherits that property. So the amplitude, the full amplitude of that process to happen is going to be given by the amplitude of the thing with the photon or photon removed times this propagator. So it's going to be minus I divided by the momentum of this. I wrote it here. This could be any of the external momentum, okay? We have N. So this could be any of those. So let me call it Pi, and I is going to run from 1 to N. So it's going to be Pi. But notice that Pi is the momenta of the final electron. So this guy here, carried away momentum Q. So the momentum of this internal propagator is P plus Q, right? So this is Pi plus Q, and then the final rule says that this propagator, I have to, am I doing it right? Squared plus the mass of the, this is the mass of the scalar field squared. I think I did it right. And now, times that, sorry about this, times now that vertex, so it's I, E, oh, sorry about that. Let me write it here. So I, E, the polarization of that photon times 2 is the momentum of this scalar particle here. So that is Pi in this case. Pi plus Q. Okay? And that's it. Right. That would be this scattering amplitude over here. Okay. We have 5 minutes. So let me, in these 5 minutes, I'm going to finish this very little computation of a scalar. Okay. So we have this times, okay, you gotta help me out here. E epsilon mu. Notice that this Q is of order omega, so this is going to go to 0. Okay? And in the denominator, I'm going to expand that product, so it's pi squared plus 2 pi dotted q plus q squared plus m squared. All right, and that's it. Okay, so notice that we said from the very beginning that these particles have to be on shelf. So that means that pi squared has to be equal to minus m squared, right? So strictly speaking, since this is the mass of the ith particle, let me be completely general, so this is going to be mi squared. So because of the particle has to be on shell, this and this sum to 0. And for the same reason, the photon is also on shell, but because it's massless, q squared is equal to 0. So at the end of the day, you get this times the coupling constant epsilon 2 t, or did it do here? This has to be a mu, and this has to be, okay? I forgot that. I forgot that. Right, next. There. Okay, so it's pi pq. No, sorry. Let me just leave it like that. And then below I'm going to have pi dotted q. Okay, the 2 goes away. So at the end of the day, the full amplitude in that limit, in the limit when omega goes to 0, when the energy goes to 0. So notice that I erased it, but since we're doing quantum mechanics, that soft photon, you have to include all the possibilities in the sense that it could have coupled to the electron number 1 or number 2 or number 3 and so on and so forth. So you have to add up all these possibilities. So it could have coupled to any of the n external electrons, and also the photon couples to the electron with a different side, with a different sign to the positron, right? And this coupling constant, let me call it E sub I, just to say that, it only has 2 possible values, plus or minus 1, or plus or minus the electron charge. But let me just keep it that way, because it's important that I keep it that way. So this is going to be EI epsilon mu pi mu divided by pi dotted into q, and all this multiplied by, or we had it, as a prefactor. Let me just write it here as the other thing. And then notice that here the momentum of the photon appears downstairs. So this is of order 1 over omega, right? So this is infrared divergent, okay? And that's how it should be. Theories with massive particles in the spectrum, even at 3 levels, should have infrared divergences, okay? Because there's a photon, there, okay? So that is an infrared divergent term, but whatever it is. This is of order 1 over omega, so the rest is going to be of order, omega to the 0, omega to the 1, omega to the 2, and so on and so forth. Okay, so that is this is the result. So let me write it in this way. Now, what we found is that in that limit, I should have written here n plus 1 amplitude. So the n plus 1 amplitude in the soft limit factorizes as a soft factor. I'm going to call it S0. This is called the leading soft factor. Times the amplitude without the soft photon times of order omega to the 0. Okay? And this S0 is this thing over here. Okay? And so this is called the soft theorem, the leading soft theorem for the case of scalar cube Now, what is the nice surprise is that Weinberg showed, and I finish with this, Weinberg showed that if you did it for QED, I'm sorry, you see, Lowe in 1958 for the case of QED found the exact same factor. But we didn't do it for QED. We did it for scalar QED, right? If you did it for any other, this is what Weinberg showed, if you did it for any other theory that has a U1 gauge field, so if any gauge theory, I mean any theory that couples to a photon, okay, this factor is going to be the same. So this is a universal thing. And this is why it receives the name of theorem, okay? So this is called the leading subtheorem, the leading subphoton theorem. Okay? And I finish with this. And tomorrow we're going to start with the fact that an amplitude should be gauge invariant. If you do a gauge transformation, which basically means that you change this epsilon by p, if you remember that, these are called the Ward identities, right? So you send epsilon, you send it to epsilon plus p, plus q, in this case the momentum of the photon, then the amplitude should remain the same. It should be invariant under gauge symmetries. When you impose that into here, we're going to find a remarkable thing, which is the sum of all the charges has to be 0. That is conservation of charge, electric charge. So just by the simple fact of assuming or that you have a photon in the spectrum of any theory that couples to light, then you will always arrive at this theorem over here, and you inevitably would get conservation of electric charge. Okay, and I finished with that. Okay.
We are a little behind the schedule for the poster session, so maybe we have time for 1 or 2 quick questions.
What is the next to leading order for this correction? You have a one loop correction, or you have more subcorrections?
That's a very good question. So it's a double expansion. Okay. So here I'm writing an expansion in the energy of the photon, but then I have to also write an expansion in the coupling constant, right? So a loop expansion, right? So what Weinberg showed is that all the loop corrections to this are 0. So at leading order, the sub theorem with which you compute just the tree level is exact. So tree level is all there is. If you go to sub-leading order, which we're going to call S1, this object over here looks a little bit different, and it has the generator of the Lorentz group, involved here. So that's going to become actually an operator, a differential operator acting on the amplitude. Okay? And that thing has corrections to one loop, but 2 and on are all 0. So that is a one loop exact result. Guess what happens at the sub-leading order? The 2 loop is that's it, and 3 loops and so on is it's 0. So it has that, and in gravity it's even more beautiful than that.
And if you put that in the optical theorem, you get something like this.
Sorry, what?
If you put this in the optical theorem that you wrote before, you get this.
With Matthias, we were trying to do sort of things. Yeah. I mean that's a natural question, right? I mean, if you input the I don't know what you get. I was trying to. Yeah, I wouldn't know exactly what. Maybe it's in the literature, right? I searched for it a lot, and there's some partial results, but I couldn't find like a final result about that. So, but that maybe it's my ignorance. So.
Any more questions? So we can thank you again.